Okay, we will discuss this very important topic of principal focus. We will be defining this term principal focus for both concave spherical mirror as well as for convex spherical mirror. Now look, this is a concave spherical mirror. Its reflecting surface is towards the center of the hollow sphere of which it forms a part. This is a concave spherical mirror. This is the center, which is known as the pole, and the line joining P and C, it's known as the principal axis, right? So let us assume this to be the point where the reflection of light is to be studied. That is, the ray will be incident at this particular point. So first and foremost, we will draw a normal over here. Now, this will act as a normal. Why? Because in a sphere, line joining the center of the sphere to any point on its surface will act as the normal. This is 90 degrees. This will act as the normal. Let us consider a ray. This is the incident ray. This is the incident ray. It is incident at point A, and this incident ray is parallel to the principal axis. So this is the incident ray, this is the normal. The angle which the incident ray makes to the normal, it will be the angle of incidence. Now as per reflection, this light will bounce back into the same medium, obeying the laws of reflection. So it will bounce back in this particular manner. This is the reflected ray. It is the reflected ray. The angle which the reflected ray makes to the normal is known as the angle of reflection. And as per the first law, angle of incidence should be exactly equal to the angle of reflection. So this is the point which is known as the focus. And point F is found to be exactly the midpoint between P and C. So PF, it is known as the focal length. PC, we are aware, it is known as the radius of curvature. So F is the midpoint between P and C. So focal length would be half the radius of curvature. Okay, now let's come across this convex spherical mirror. Here, this is the convex spherical mirror we have discussed. It's also a part of a hollow sphere. This is a part of a hollow sphere. You need not to draw it, just it's an illustration for you. This is a part of a hollow sphere. Its center will be somewhere over here. This will be the center of curvature. This is the reflecting surface, right? And this will be the center. This is the reflecting surface, away from the center of this hollow sphere. So line joining P and C will act as the principal axis. Suppose this is the point where the light will be incident. So in order to draw the ray diagram, first we need to draw normal at point A. So as I told you, any line from the center of the sphere to a point on its surface will act as a normal. This will act as a normal because this line is perpendicular to the surface over here. Now what to do is, this is the incident ray. This is the incident ray, which is parallel to the principal axis. Now, the angle which the incident ray makes to the normal is known as the angle of incidence. This will be the angle of incidence. It is coming from this particular medium. So it will bounce back into the same medium on the other side of that of the normal, obeying the laws of reflection. So it will reflect back into the same medium like this. This is the reflected ray. This is reflected ray. And the angle which the reflected ray makes to the normal, it is the angle of reflection. These two angles must be equal as per the law, right? So if you produce this reflected ray in the backward direction, it will appear, this reflected ray will appear to be coming from this particular point on the principal axis. So this point is known as the principal focus. As I told you, the distance between the pole and the focus of a mirror is known as its focal length, represented by small letter f. And the distance between P and C is known as the radius of curvature. F being the midpoint of P and C, therefore focal length is equal to half the radius of curvature. There is a mathematical verification for this as well, right? So now in the next section we will discuss concave mirror is also known as a converging mirror, while convex mirror it is also known as a diverging mirror. So basic reason behind this, again I will illustrate with the help of a simple diagram. So first we'll discuss the statement concave mirror acting as a converging mirror. So concentrate on this particular diagram. Again, this is a concave mirror. It's a part of a hollow sphere. Its center would be somewhere over here, right? This is the center known as the pole. This is the principal axis. Now what happens is, when a parallel beam of light is incident on it, earlier we have considered a single ray, right? Now we are considering a parallel beam of light to be incident over here. This is a parallel beam of light. Now what happens is, after suffering reflection, we have discussed the reflected ray tend to pass through a point on the principal axis. So after suffering reflection, all these rays will tend to get converged at a particular point on the principal axis. All these rays will tend to get converged at a particular point on the principal axis. And this ray, this is the normal at point P. So incident ray is making an angle of 0 degree with the principal axis. So the ray after reflection will retrace its path in the opposite direction. So all these reflected rays are converging at a particular point. This point on the principal axis is known as principal focus. It is converging. So that is the reason why concave mirror is known as a converging mirror as well. So the reason concave mirror is known as a converging mirror because when a parallel beam of light is incident on a concave mirror, then the rays after suffering reflection tend to get converged at a particular point on the principal axis. This particular point is known as the principal focus. So concave mirror is also known as a converging mirror because it converges the reflected beam at a particular point on the principal axis. Similarly, we can justify that convex spherical mirror is also known as a diverging mirror. So for that also, the statement can be justified with the illustration of the simple ray diagram. This is a convex mirror. This is the pole. It's a part of a hollow sphere. The center of that hollow sphere will be somewhere over here. The line joining P and C is known as the principal axis, right? Now what happens is, a parallel beam of light is incident on its reflecting surface. This is the reflecting surface bulging outwards. This is the reflecting surface. A parallel beam of light is incident over here. So what happens is, in this case, the rays after such reflection, it will bounce back into the same medium, right? So the diagram would be somewhat like this. It will bounce back into the same medium. And this incident ray, it is coincident with the principal axis, so angle of incidence is 0, so the angle of reflection will also be 0. So these rays, when you produce them in the backward direction, they all will be appearing to be coming from a particular point on the principal axis. And behind the mirror, it is to be represented by dotted lines. So this point is known as the principal focus. So basically, in this case, when a parallel beam of light is incident on the reflecting surface of convex mirror, then the rays after suffering reflection appears to be coming out from a particular point on the principal axis. This particular point on the principal axis is known as principal focus. So concave mirror, it converges the reflected ray, while convex mirror, it diverges the reflected ray. This is the very reason why convex mirror is also known as a diverging mirror. It is also known as a diverging mirror. And as I stated earlier, the distance between P and F is known as the focal length. The distance between pole and the center of curvature is known as the radius of curvature. And it can be easily proved that F is the midpoint of P and C. Therefore, the mathematical relationship between focal length and the radius of curvature is F is equal to R by 2. So this formula is valid both in the case of spherical mirrors as well as in the case of plane mirror. Can I ask you a question? What will be the radius of curvature of a plane mirror? Plane mirror, its surface is plane, it's not curved. Plane, it should be infinite. I'll give you the reason. Consider a hollow sphere and a very large radius. Then a small part of the hollow sphere will act as a plane mirror or a plane surface. So in that case the radius is very, very large. So for a plane mirror, radius will approach to infinity, and accordingly focal length being r by 2, it will approach to infinity. So the radius of curvature or the focal length of a plane mirror is infinity. So this formula is valid for spherical mirrors as well as for plane mirrors.